Now we are going to move to chapter 6, residues and pores. The last time we have learned Cauchy theorem in section 50. The theorem says if a function f is analytic at all points interior to and on a simple closed contour C, then we have the result integral along to contour C fg dg equals to 0. So the theorem shows that how to compute the integral of a given function and a given simple closed contour C. Let's see another big theorem. Cauchy integral formula in section 54. Theorem says let f be analytic everywhere inside and on a simple closed contour C, taken in the positive sense. If G0 is any point interior to C, then we have the result f of G0 equals to 1 over 2 pi I times integral along to contour C fg dg divided by G negative G0. When we modify this result, this equation, so I mean that the integral first. So integral along to contour C fg dg divided by G negative G0 is equal to 2 pi I times f of G0. So it also provides a method to compute the integral. Now we have another theorem, which is the extension of the Cauchy integral formula in section 55. Theorem says let f be analytic, same condition, same prerequisite, like the Cauchy integral formula. But we have the nth derivative of f at G0 is equal to n factorial divided by 2 phi I integral along to contour C fg dg divided by G negative G0 to the n plus 1 powers. Here n is non-negative integer. Just the theorems I said are requires or analytic, so for the given function. But now we wonder, however, if the function f fails to be analytic at a finite number of points interior to C, how to compute the value of the integral of the function around that contour C. In order to deal with this case, we study a specific number called residue and the theory of residues. From this, we know that each residue contributes to the value of the integral. Before we are going through the details for the residue and the theory of residues, we first look at some examples, some definitions, singular points, isolated singular points. In section 24, we record that a function f is analytic at a point G0 if it has a derivative at each point in some neighborhood of G0. We also there Another notion, a point G0 is called a singular point of a function f if f fails to be analytic at G0, but is analytic at some point in every neighborhood of G0. Especially, a singular point G0 is said to be isolated if there is a deleted epsilon neighborhood given by this. G negative G0, absolute value of G negative G0 is greater than 0 and less than epsilon of G0 throughout which f is analytic. So you can here G0, and so G is, if G is given, then we can compute the distance between 2 points. So G, but this distance is upper bound by epsilon. And also, G cannot be the point G0. As the main subject of discussion, the theory of residues in this chapter has the special type of singular point, that is, an isolated singular point. Let's see the examples to see the isolated singular point. Example 1, the function given by this f of g is g negative 1 divided by g to the power of 5 times g squared plus 9. As the 3 isolated singular points, that is g is equal to 0 and g is plus minus 3i. Singular points of a rational function, which is made by a quotient of two polynomials, are always isolated because the zeros of polynomial in the denominator are finite in number by the fundamental theorem of algebra, which we have learned in section 58. We revisit that there. The fundamental theorem of algebra says any polynomial p of g is a0 plus a1g plus a2g squared plus plus an times g to the n. Here, an is not equal to 0. Of degree n has at least one 0. That is, there exists at least one point g0 such that p of g0 is equal to 0. The fundamental theorem tells us that any polynomial p of g of degree n, here we assumed n is assumed to be greater than or equal to 1, can be expressed as a product of linear factors like this, where c and gk are complex constants. It is clear that p of g can have no more than n distinct zeros. So if we choose a pair of gk, for example, we have g1 and g2, then we assume that these 2 points are distinct, which means that not same. Then there is a distance between 2 points, if we take epsilon as half the distance between 2 points, then G1 is a singular point when we consider some rational function but particularly the denominator has 0 as gk here, because we can have a deleted epsilon neighborhood like this, throughout which f is analytic. Because we consider a quotient, so the denominator is a polynomial, but polynomial is entire, so this definition is satisfied.